All right, hello class. We're going to be working today on the independent samples t-test. So if you have two samples, right, and you have hypothesized population that these samples are coming from, but you only have available the two samples, you'll be able to test for significant difference and make decisions based on which treatment you find to be preferable, or maybe you just want to just for exploration, your reasons you just want to have a discussion of significant difference, you'll be able to run this test. All right, so in order to work along with us, you should have either some scratch paper or use of Microsoft Word or Notepad, Excel, and JASP. Again, we're going to be using JASP for our computations. And then I'm going to also show you how to compute your T and test using just the formulas and, maybe Excel and a calculator to kind of work you through or speed you through the process. Okay, so I'm going to start with an example. You find the example is pretty relevant, all right, to the culture. So we're going to just read this example and just follow along, just listen along, because I'm going to present the data afterwards. All right, so McAllister and colleagues compared varsity football and hockey players with varsity athletes from non-contact sports. All right, so we're going to compare some contact athletes with non-contact athletes. We want to determine whether exposure to head impacts during one season have an effect on cognitive performance. In the study, tests of new learning performance were significantly poorer for the contact sport athletes compared to the non-contact sport athletes. All right, so we have some data that's going to that I'm going to present. All right, similar to the results obtained in the study, but we're going to take our data and see if we can confirm McAllister and colleagues' findings from 2012. All right, so we have two independent samples, and we're going to be able to test. And so, but first, I want to go over just some pointers about running the independent samples t-test and some things you should be looking for or taking care of. So let's share the screen with you all so you can quickly look at just two PowerPoint slides. Won't spend too long there. All right, so first you have to make sure when we have independent samples that the behavior of members of one sample is not related to behavior of members of the other, right? So in our case, we have contact sport athletes and non-contact sport athletes, and we're testing cognitive performance. That, the variable, whether it's their contact sport performance or a cognitive performance, right, we don't see any relation between the two. We assume independence as long as the subjects are selected at random from a large group and assigned randomly. So I could think of as a problematic situation in terms of independent samples, perhaps if I was running a sleep study and I had a treatment that was going to aid individual sleep, and then I'm selecting individuals maybe from a pool at a university, and I wish to place the students who tell me they're sleeping longer than 8 hours in the treatment group that's going to receive the sleep aid, and then those who sleep less than 6 hours I can place in the control group. I mean, of course, I'm messing with the data, and right, I don't have independent samples necessarily. I'm not assigning randomly. All right, so in fact, I would probably want to consider running a match samples t-test if I'm looking to sort of have a match where, let's say, we'll have individuals who have difficulty sleeping or sleeping less than 5 hours. Maybe I'll place two of those individuals into the study and separate them, right, with treatment and control. So that's something that we're going to discuss in another video. But we want to make sure that we have independent samples here when we're running the independent samples t-test. And again, we're assigning randomly. Also, we want to make sure that our samples coming from populations that are normal, right? And then that we have homogeneity of variance. All right, so we don't want to find a significant difference between the two variants. We can test this with Hartley's F max, right? And we're not going to go into that. And I believe JASP does not have that as part of the program yet. But again, you want to consider the homogeneity of variance, right? But for our case, we're going to just compute a T, see if we can find an effect size, and then we're going to make a decision about the null hypothesis. Okay. So let's get to our notes. I'm going to state the hypothesis. The null states that, and I can enlarge this, that may help. The null states that there's no difference in cognitive performance between non-contact and contact athletes. All right. And that's what we see listed here. The population mean 1 is equal to population mean 2. If we were running a one-tailed test, we would write this as population mean 1 is less than or equal to population mean 2, basically saying that the non-contact athletes are going to perform worse than or equal to the contact athletes. Basically, you're giving space for all results other than the alternative, which would say that the contact athletes, or I'm sorry, the non-contact athletes are performing better than the contact athletes. Talking about a one-tailed test. But I want us to just focus first on the two-tailed test that you see denoted with the equal and not equal sign. So the null hypothesis states that there is no difference. The alternative hypothesis states that there is a difference between the two groups. Okay, so here's the data that we have, because we're going to move from our criteria that we're going to go over in a bit, from our criteria to collecting the data. So the data is here. You can kind of take this data down if you wish. You can copy and paste quickly. But I want us to consider our criteria first. I'm setting the criteria, two-tailed test set at 0.05. Degrees of freedom is 14, and this is why I quickly wanted you just to look above. We have 8 individuals in each group. When you're running an independent samples t-test, your degrees of freedom is equal to n1 plus n2 minus 2, or n1 minus 1. Maybe I can write that quickly. So we have n1 minus 1 plus n2 minus 1. That's going to give you your degrees of freedom. Let me clean this up a little. So if n1 is equal to 8 and n2 is equal to 8, we're going to have 7 plus 7 equal to 14. Okay, you can keep that formula up for your own use. Okay, so degrees of freedom is set to 14.05. That's going to give us a critical t value of 2.145. So after we compute t, we're looking for a t value that's going to be greater than t in order for us to reject the null hypothesis. All right, I'll also put in notes for the one-tailed test. You have to have a t value that's greater than 1.761. We know our one-tailed test would have more power, right? Because we're placing our critical region on one side of the distribution. All right, so you collect data and compute the sample stats. All right, so we should have a t compute for degrees of freedom 14 after we place this data into JASP. All right, so here's our data, non-contact athletes and contact athletes. All right, so I can copy and paste the data here. For the contact athletes, we're going to use a number 2. For non-contact athletes, we'll be using number 1. So you can just copy and paste the data, right? And you're going to create a column called contact. All right, so non-contact athletes will receive a 1, contact athletes will receive a 2. For the first column, you can call it cognitive performance or scores, that's up to you. If you don't feel like copying and pasting, just go one by one, type them in, and just, shift your screen so you can read both screens at once. Take some time and get this done. And then we're going to save this file as an ODS file. We know that's how we can read JASP, or JASP can read Excel. Okay. All right, so I'm going to, I think I already have this saved. I'm going to just go through the process so you can see it. ODS is towards the bottom. Save, I wrote contact sports as a label. Already exists, yes, I'm going to replace it. Okay. We open up JASP. For those who don't have JASP, open source, you can download it. This is jasp.org, I believe. Right, just do a Google search. It's free. And they say it's free, friendly, and flexible. Okay, recent files, contact sports. But here we are, we have our information listed. We can run our descriptors. So always good to run the descriptors. Cognitive performance variable, contact. We're splitting the variable cognitive performance by contact level. 1 is non-contact, 2 is contact. We can see our means are different. We're going to go mean, median, mode. We'll also go standard deviation, variance, range. Okay, so you should be able to see these stats up here. Standard deviations look somewhat similar. All right, variance isn't terribly different either. Okay, and we're going to get to our t-test, independent samples t-test. Again, cognitive performance. We have our grouping variable, contact level. Let's see if we can get Cohen's D up here. Okay, so we have a Cohen's D level, 1.22. All right, so we're looking at a large effect size, a large treatment effect size. And I'm sorry, the alternative hypothesis listed here, we're using the two-tailed test. So we have group 1 is not equal to group 2. We're going to plug this in for the one-tailed afterwards. We see a probability of 0.041, that's less than 0.05. So we have significance. Let's get back to our worksheet. There is a difference in cognitive performance between non-contact and contact athletes. We're going to reject the null hypothesis. Okay, so our decision is made. Okay, and we have our T computed. We can place that in as well. 2.245. 2.245. All right, so let's just take a quick look at the one-tailed test. Group 1 greater than group 2, right? Because we're expecting greater performance. We have 0.021. So we would not be able to reject the null at the 0.01 level, which would be, that's an even stronger statement to make. So in this case, I mean, again, you can report as a one-tailed test, and you can state that non-contact athletes have significantly greater cognitive performance. You could say that on a particular test, right? We don't want to just speak overall, like globally, but on this particular assignment, you can say that. but you really can't use 0.01, you know, as your rejection point. Or in order to, you cannot reject the null hypothesis at the 0.01 level or alpha set at 0.01. All right, so these are our findings. So, I mean, this is it. This is enough to answer the question. If you don't wish to use JASP, how would you go about this? Okay, so now we're going to add some more steps. We're going to talk about, right, just the T, the value of T, and the formulas. And I'm going to show you how you can compute T using this data. So I'm going to go back here. I'm going to remove this column. And I'm going to so we're going to change. So we're going to say non-contact group. Again, I don't advise you all to not use JASP or SPSS, but it's, you know, sometimes it's good to just see, you know, where the numbers are coming from. So if you remember, your formula for T was equal to sample mean minus population mean divided by square root of variance, right? And we're talking about the variance of the sample variance divided by sample size. All right, so your estimated standard error is coming in your denominator, is coming from function of your variance and sample size. Or you could say standard deviation over the square root of sample size. It's up to you. In this case, we have two different samples. So we're going to compute what is called the pooled variance, right? The pooled variance, right? So I'm going to show you how we get there. Let's just see if I have some of the information below. Yes, okay. So our formula for T is going to be equal to, I just want to slide this over so this looks correct. T is going to be equal to the difference between the sample means, a sample mean 1 and 2. And that difference is going to be divided by the estimated standard error of differences. All right. You see the symbols, the differences of between mean 1 and mean 2. Talking about standard error, right? The expected difference from one score to another, the sample mean from one sample mean to another. Again, we're estimating from the population, right? Even when we look at our numerator, we're using sample means, but it's really an estimation of the population from which these samples are coming from. Because we're estimating, we're using T. All right, so when I mentioned the pooled variance, if you consider that with the one sample t-test, you're taking the square root of variance over n, well, now we're going to pool that variance. So in order to pool the variance, we're going to use the sum of squares divided by degrees of freedom, which is how you get the variance, right? N minus 1 below the sum of squares. But we're going to take the sum of both sums of squares, and then we're going to take the sum of both degrees of freedom, and that's going to give us the pooled variance. Once we have that pooled variance, we will then take the square root of the pooled variance over n plus the pooled variance over n. So just imagine you're taking the square root of variance over n, but you're doing it twice for each sample. All right, so we wish to run this test by hand, so to speak. It's not by hand, we're using Excel kind of to speed along the process, but let's just run this and see how it goes. So I want to have both screens available. Okay, this works. Hopefully this isn't too cumbersome for those watching. All right, so we need both means, right? We need the average for both. We have the non-contact and the contact group. So users, for my Excel users, for those who aren't familiar, in a function box, I'm going to pick A11 to write the average in. So you write equal average, and then they're going to ask, the system wants to know where's this average coming from A2 colon through A9. All right, so that gives us an average of 9. And we can look back at JASP because we already have our means 9 and 6. All right, so just going to write 6 in for the contact, but I at least wanted to show you how you can just run the function quickly. All right, so we have our two means. We have 9 minus 6, which is going to equal 3. Okay. So now we have to get to the, the longer, the more mentally strenuous, or you could say tedious work. We want to find the sum of squares for both sample 1 and sample 2. And we can find that, and I'm going to use A13 for the first sample, and that will be equal deviation squared. Again, that's going to be A2 through A9. It gives us 44. Okay, it's underlining, remove that. Oh, okay, it's fine. 44 plus deviation squared for sample 2. Again, in the function box, equal deviation square. That's going to be C2 colon C9, 56. Gives us a neat number of 100. We're going to have 100 in the denominator. Degrees of freedom, we have eight minus 1 twice. So 7 plus 7, that's going to be 14. Also over here, we have 100. Sorry, I'm having. Okay, so our pooled variance is going to be equal to 100 divided by 14. Let's plug that in. Okay, I got 7.14. We can hold it there. Maybe 7.14 is our pooled variance. We're going to use that number twice. All right, so we already have our numerator figured out. That's mean 1 minus mean 2 is equal to 3. So now we need to take the square root of pooled variance over N1 and pooled variance over N2, right? We have equal sample sizes, so we're going to have the same number added to each other. So let's move down below. 7.14 divided by N, which is going to be 8 in this case, plus 7.14 divided by 8. We're going to take the square root of this sum. Okay, so 7.14 divided by 8, 0.0892. 0.089 plus 0.089 gives you 1.78. And I'm sorry, I think I misspoke. It's 0.89. All right, so not 0.089, 0.89. All right, so you have 0.89 plus 0.89. I'm going to take the square root of 0.89 plus 0.89. So we're looking at the square root of 1.78. All right, and that's going to finally bring us to our estimated standard error of differences between the two sample means. All right, so you can punch on your calculator, or you can even work through Excel. You can run your square root. Let's see. I'm sorry about that. I'm doing something wrong here. All right, so we have 1.334 or 1.33. And that's going to be our estimated standard error. I'll just check it again, make sure I'm doing this correctly. Okay, so I use multiple calculators. So we use an Excel. You just put the number in. You can put equal square root, and then in your quotations, you can put the number you wish to find the square root of. So we have our estimated standard error of differences, and we have our mean differences. So we have 3 over 1.33. 3 divided by 1.33. We can quickly punch that in. Gives us, I have 2.55. I guess that would be 2.255, which I can round to 2.26. So T is going to be equal to 2.26. Again, we have our critical T value that we're comparing this T to. And the critical T value was 2.145. I computed 2.245. And, running this data, again, not as exact, right? I'm rounding off at the 100th place, but I have 2.26. for my t-value. So I'll still be able to reject the null hypothesis. Not much has changed here. And this is just the longer way. Again, I may have moved a little bit slower just for training purposes. But again, if you're working by hand, you need to move slow anyway and check. Notice there were some areas where I stated or misstated 0.089 when it was 0.89, you know, although I had it written correctly, these things can be written incorrectly. So there you have it. That's your independent samples t-test. If there are any questions, you know, you can drop the questions in the comments, or, you know, just work them out. I have my email address as well. And for my students, you know how to contact me. All right, so take care and see you soon.